Okay, let's start my lecture on science for food safety. I am Toru Watanabe, a professor of faculty of agriculture, Yamagata University. This lecture has two contents. The first content is risk analysis for ensuring the food safety. Incidents that undermine food safety are still frequent, but for matters that are scientifically understood, measures are being taken to protect human health. I will introduce how these measures are implemented. Actually, you can get the more detailed information on risk analysis in another lecture, Global Environmental Risk Analysis. So if you are interested, please take this lecture later. The second content is food safety challenges, norovirus contamination in oysters. Even when science has clarified a problem, our current technology sometimes makes it difficult to deal with it. I'd like to give you one example. Okay, let's start with the part one, risk analysis. So I'd like to explain about the definition of risk at first. The present Congressional Commission on Risk Assessment and Risk Management in the United States defined risk is the probability that substances or situation would produce harm under specific conditions. Risk is a combination of two factors: the probability that an adverse event will occur and the consequences of the adverse events. So we have the different words which has a very similar meaning to risk, that is hazard. But the difference from hazard to risk is quite, I can say, clear. The hazard is determined by whether a particular substances or situation has the potential to cause harmful effects. On the other hand, risk does not exist if exposure to harmful substances or situation does not or will not occur. So you may understand that this difference is more easily with this schematic. So hazard always exists if that the substances or situation are harmful. That's why we can make the same circle in left and right hand side schematics. But we are, I can say, here as target population, we have a enough distance from the hazard. We will not have the risk. But once we approach to the hazard, we may expose to the hazard. This situation result in the risk. Left-hand side schematic shows that no risk because there is a sufficient distance from target population and hazard. But in the right-hand side schematic, the target population are, the close to the hazard. Some of the population had exposure to the hazard, resulting in the considerable risk. Okay, you can compare one another based on that. I can say two schematics. Okay, I'd like to introduce the history of risk assessment. In 1960s in the United States, Food and Drug agencies employed tyranny clause to prohibit the use of any amount of carcinogenic substances in foods in Food, Drug, and Cosmetic Act. Carcinogenic substances is the substances which can cause in human being. Okay, they aim to establish a zero risk, no risk, caused by the carcinogenic substances in food under this act. However, after employment of this, clause, they faces several problems. First problem is that advances in technologies enabled detection of carcinogenic substances existing in foods at low concentration. In the past, they couldn't detect the carcinogenic substances at low concentration, but the development of the technologies enable them to detect such harmful substances. The contamination of food were not changed, but technology to detect the contamination had been developed. That's why how can I say, they noticed that their food were contaminated by the carcinogenic substances widely. Second problem is that no evidence to support suitability of applying zero risk demonstrated in lab animals to human. I will give you the more detailed information about this later, but we can get the data supporting the zero risk only from the lab animal because we cannot, I can say, test human with such harmful substances from the ethical, reason. I guess you understand about this well. But some people didn't, believe the zero risk demonstrated in lab animals was applicable to human directly. And the third problem is that achieving zero risk for substances sometimes cause risk for other substances. So I'd like to, I can say, give you one example. The sugar versus saccharin. The saccharin, all of you, I can know sugar well. And I guess some of you know the name of the saccharin. Saccharin is the artificial sweet. Okay, it was developed for people getting the diabetes. So the diabetes patient, should reduce the consumption of the sugar to avoid the development of the symptom. Okay, the consumption of the sugar should be controlled well for their health. But they want to eat the, how can I say, sweet food or sweet drink. Then some chemical company developed this material, this, how can I say, the chemicals, saccharin, which can be used, as a proxy of the sugar. Okay, it brings the sweetness, and it didn't increase the, how can I say, sugar concentration in blood. And they, how can I say, the diabetes patient was very happy to, consume the saccharin instead of the sugar. However, some scientists, not, how can I say, not found a risk of the cancer caused by the saccharin. A little bit later after the development of the saccharin. And this means that, I can say, the consuming the saccharin instead of sugar surely decreased of the risk of the diabetes. However, it increased the risk of cancer. So this is one example, related to the problem number 3. Achieving the some risk, cause another risk. We call this relationship, risk trade-off. But anyway, such problem, how can I say, found after the Delany clause, employment. So these problems, I can say, made the policy maker decided to give up applying the Delany clause to the foods. It's not realistic. It was not realistic or not cost effective at that time. Then in 1977, almost 10 years later, the FDA revised the act and employed the cancer risk level of 10 to the power of minus 6 to be ignored. So I hope that you, I can say, easily found the difference between that new or revised act and original act. The original act targeted the zero risk, no risk, but revised act accept the non-zero risk. Okay, more more detail, 10 to the power minus 6. This means that, we should accept the one person in million get cancer due to the, I can say, some, carcinogenic substances in food. Okay, if someone had the higher risk than 10 to the power minus 6, they do not need to accept, but the risk lower than 10 to the power minus 6 should be accepted, should be ignored. So you may feel that the 10 to the power minus 6 is quite small. It's the almost I can same as 0, but there is a big difference between 0 and 10 to the power minus 6. Okay, then uh, this acceptable risk has been I can say employed in the other I can say act uh, like I can say like the Occupational Safety and Health Act, Clean Air Act, and Toxic Substances Control Act. So anyway, there is a lot of the act to control the contamination of food, air, water, I can say the labor environment, and so on. In these acts, it is not realistic to, target the risk. Okay. Then they decided to, introduce the acceptable risk as a goal. But actually that they use that different words. For example, adequate margin of safety, reasonable necessary of appropriate, ample margin of safety, as low as reasonable achievable. So it's I mean that there is I can say a slight differences in that terminology, but meaning are quite similar. That risk should be accepted. In other words, acceptable risk. Okay, so the act employ that such non-zero acceptable risk in the history. Then, based on that acceptable risk, I can say the policymaker frequently conduct a risk assessment. So this is the framework of the general risk assessment. So risk assessment requires the 3 steps and one additional steps. The first step is the hazard identification to answer whether a substance is harmful for human health or not. The second step, dose response assessment. In this step, we had the question: can the occurrence of damages be quantitatively related to the dose of the substances? And third step, exposure assessment with the aim to answer how is the present exposure to substances and how is that in other settings. So based on the result of these 3 steps, so we can make the risk characterization to answer how is the occurrence possibility of damages for population. Okay. Then the characterized risk will be compared with the acceptable risk, which I have already introduced you. Okay. The acceptable risk, I showed one example. The cancer risk, risk of cancer should be accepted 10 to the power minus 4 it's the acceptable risk for cancer risk. But it is just one, I can say, example. The acceptable risk should be, dependent on the substances or situation. And the acceptable risk will be determined uh, by the social agreement from the viewpoint of public health, economy, and politics. And this acceptable risk, should be, checked or advised, and sometimes discussed with the consensus, exposure population, mass communication, politicians, researchers, and so on. So this step, revise or I can say modified acceptable risk process is called risk communication. I guess some of you heard have heard about the risk communication. And finally, the acceptable risk uh, determined through the risk communication used to be compared with the risk characterization. And for example, the character risk is exceeding the acceptable risk. There are some, I can say, the policymaker makes something to reduce the risk. Government may make some new policy to reduce the risk because the character risk is higher than the acceptable risk. And of course, the characterized risk is much lower than acceptable risk. Okay, we should accept that situation. Okay, that's why we, I can say, call that the decision and action on the policy. I can say the following this comparison between the acceptable risk and actual risk. Okay, from now on, we'd like to show you that how to make the risk assessment step by step. Okay, the risk assessment, especially the quantitative Q means the quantitative risk, R is risk, A is assessment. The QRA quantitative risk assessment, the process to estimate the number of patients of specific diseases from the pollution of water, air, and soil environment. Okay. So at first, we need to make the dose response assessment based on the exposure test to lab animals. So as I already mentioned in the previous slides, so we cannot how can I say perform the exposure test of harmful substances to humans. Instead, we use the lab animal like rat, mouse, guinea pig, hamster, and so on. So in the such lab test, we inoculate such small animals. I can say at given dose, for example, 100, 1,000, 10,000, and so on to each individuals. Okay, and we observe I can say if some symptom occurred or not. Then we can get the result. For example, under the dose of the 100, only one animal shows a symptom among 10 individuals, and another 1,000 those, 3 of 10 animals shows the symptom, and 10,000 resulted in the 6 positive, 100,000 9, 1 million, all under the 1 million, all animals were positive. Then we can put these results on the figure with the dose and positive percent like this. So this, I can say, plot the showing that relationship between the dose and response. Okay, positive percent is a kind of the response of animals. Okay, so we can use the dose response data, shown by plot in 2 different ways. The one way is for the substances with threshold following this line. So as you can see, the response or risk decrease with the decrease in dose, and finally it reaches 0 and here, and we can see the dose less than this level give us the 0 risk, okay, no risk. So this is the first case. The second way is following this line, okay. Same as the similar to the first group. The risk is decreasing with the decrease in dose, but this line never leads to the 0 risk. Okay, even the very small amount of the dose, very small dose, can cause the adverse effect at a quite low risk, but no risk. Okay. This case, first group had the threshold reaching 0 risk. The second group doesn't have that threshold. In other words, this type, the second group has never reached to the 0 risk, even I can say if the dose is quite small. And the first case, first group with threshold, the risk of the first group with the threshold can be assessed using this equation. The lower is no observed affect level, or lower is the lowest observed adverse effect level. They are, I can say, obtained in the lab animal test, and lower should be divided by the uncertain factor to get the TDI, a tolerable daily intake. So this is one example of the lab animal test results. Okay, so as I already introduced that in the lab animal test, the different dose of the target substances are given to the animals, and they are changed. Okay, the symptom development of symptom of the animal will be, how can I say, carefully, observed with time. Then you can see that, at the, how can I say, the those of the 10, the no animal showed the symptoms. Then we determine that 10 at the Noel, and also that that 100 at the dose of 100, we can get the positive animal. You know, then that we can determine that 100 the no as lower. And the uncertainty factor should be determined, considering these factors. Uh, for example, explanation from the data of Arab animal to humans. So, as in the past, someone did not believe that zero risk for the how can I say demonstrated in a lab animal were applicable to human. So it is the same meaning. We cannot easily believe that data obtained in lab animals could be extrapolation to humans. Especially that we use that a very small animal like a mice and rat, that we suppose that significant difference of the body weight, or I mean the system uh, uh, among how can I, between the species. Okay, then even in the same species, we may how can I say notify. We may find the diverse in sensitivity of each individual. Some animals, I can say, are very sensitive to the target substances, but the others are not so sensitive. So it's the, I can say, individual differences. Okay, and we also consider the validity of experimental method. The we believe the results of test using the large number of the animals. Okay, and we believe that the result of the experiment with the same inoculation route, I can say, which we are exposed to that target substances. And we also believe the experiment for a longer, how can I say, exposure time, and so on. And some health effects are not actually the well understood. Such I can say the evidence of the health effect are another factor, uncertain factor, and severity and effect to multiple generation are also the should be considered when we discuss about the uncertainty in the dose response. Okay, and we put the uncertain factor 1 to 10 for each factor from top to bottom, and overall, overall uncertain factor is calculated by the multiple all factors. For example, if the all factors had that 10 as individual uncertain factor, the overall, uncertain factor is calculated by 10 by 10 by 10 by 10, 10, 10, resulting in the 10 to the power of 6. It means that 1 million. Okay, Then if overall uncertain factor is larger than 10,000, the TDI is not approved or used as provisional value. Okay, it's not the official one. Then, TDI could be, calculated by dividing the lower or lower by overall the factor. Then if the daily intake of the target substances is less than TDI, we do not consider the risk. I mean, no risk. It's very simple. Okay, we'd like to, discuss about the second group without threshold. So this group mainly, include the carcinogenic substances which can cause the cancer in human. Now, what is the carcinogenic substances? The substances is categorized into that, five category by IARC. Okay. Category one, including the benzene and arsenic, with the proof of the carcinogenesis for human and lab animals. Okay. So category 2A, including the formaldehyde, aldehyde, and cadmium, which has the clear evidence for carcinogenetic in lab animal, but the limited evidences of carcinogenetic in humans. And category 2B include the chloroform and CBN TET, supported by the limited evidence of carcinogenetics in human and lab animals, like this. So, and category number 3 and 4 actually no, we do not, I can say, apply the risk assessment method, without threshold, because there are, not enough evidence for carcinogenetics for these, substances. Okay. Then the risk of these carcinogen substances can be assessed, okay, with the dose response model. I can say that it's the mathematical function or equation based on that several, I can say, theory or assumptions. For example, these three models, probit, logit, Weibel models, were based on the distribution of human tolerance to carcinogenic substances. Okay, you can see that D is the dose and PD is response. Okay, the logit and Weibel has also the equation to calculate the PD, probability of cancer based on the dose. These three models, multi-stage models are based on the mechanisms of genetics in human body. Okay. These models also had the D is at the I can say independent variable, and PD as the dependent variable. Okay, I'd like to give you that one example of a risk assessment in this way for a risk of kidney cancer caused by chloroform. Okay, please look at this small figure. This figure shows the relationship between dose and the response at the probability of cancer development. So you can see the 5 circles in this figure. These circles mean the result of the lab animal test challenged with the dose of the 5 different levels, from 0 to 160. And the four those response model, log logistic, multi-stage, viable, and log profit models were applied to these 5 data points, and all of the 4 models demonstrated the comparable goodness of fit to the 5 data, as shown in this figure. Then please look at this circle corresponding to the dose of 0. In this case, even when the no chloroform were applied, a part of the lab animal showed the kidney cancer. Okay, we can say that clearly it was not attributed to the chloroform. Okay, the lab animal had the potential to develop the kidney cancer for another reason. So we can say that this is the background, and the excess risk were calculated over the background in the bigger figure. So this is the level of the background risk between the 0.1 and 0.01. Okay. Then this bigger figure also shows the relationship between the dose and response, which is the excess risk over background. Okay. But the dose level were smaller than the previous small previous figure. And you can see that the different, I can say, big differences in the risk, calculated by the these 4 models. So this is because that these areas were, I guess, corresponding to the very low dose. We thought the comparable goodness of fit to the data among 4, I can say, models at the dose level of the 20 to 160. 20 to 160 is around here. Okay. Even in this figure, that these 4 model demonstrated the comparable goodness of fit in this dose level, but in the level smaller level of the dose, the risk calculated by the model were totally dependent on the model. Okay, the highest, for example, the corresponding to the dose of 1. The highest risk were calculated by the multi-stage model at the 10 to the minus 4, and the smallest one are led by the log profit model at the 10 to the minus 7. The difference is 1,000 times. Very, very big different result are obtained. One model to another. But normally that we cannot decide which model are best. In such case, we use that average or ensemble mean or some technique to make the average considering the I can say equality of the I can say its values. Okay, this is because I can say that each model has the I can say each justification or I can theory or assumption which can be accepted by the like experts. No one can make decision which is best or which is second, third, and last. So, okay, this figure shows that WHO drinking water quality guideline, which were developed using the dose response model, which I introduced here. Okay, so you can see that many I can say the harmful substances in drinking water. For example, benzene, bromoform, carbon tetrachloride. Okay, and you can see that bromoform, NOAL at here, and TDI 70.9. And you can also see that uncertainty factor of 1,000. So based on these values, Bronholm concentration guideline are determined as 0.1. So in similar way, in the same way, the guideline value for carbon tetrachloride at 0.002, smaller than Bronholm mean that this carbon tetrachloride has the higher toxicity than Bronholm. Yeah, the difference of the toxicity are I can say found in the NOAL and TDI as well. And these two substances were, I can say the risk of these substances are assessed in the first way with the threshold. On the other hand, benzene, chloroform, and 2,4,6 trichlorophenol were, so the risk of these harmful substances were assessed in the second way without threshold. And that this case, I can say that the guideline value are calculated based on the acceptable carcinogenic risk, as 10 to the power minus 4 or 5. Okay. So this drinking water guideline were used for setting the drinking water quality standards in a lot of the country, including Japan. These guidelines are determined based on that, the risk assessment in the two different way, okay, with threshold and without threshold, as I taught today. Okay. So I'd like to give you that one, I can say, limitation, or I can say the difficulty to apply these risk assessment method to a specific, I can say, a group of the harmful substances. So you can see that, I can say the table, big table, written in Japanese. I'm sorry, but this, table shows the variety of the human pathogens existing in human intestinal tract. So, for example, Salmonella, Shigella, Vibrio cholera, Leptospira, Escherichia coli, Campylobacter, amoeba, and so on. So, some of you do, never heard about the name of the bacteria or pathogenic viruses, but we have these, I can say, pathogenic bacteria or viruses in our intestinal tract. Okay. Actually, a lot of the species of the bacteria are found in the human intestinal tract. Then, if we want to, I can say, if you want to, assure the safety of the again food and water is free of these pathogens, we need to, detect. We need to try to detect the pathogens, in that food and water one by one. So simply speaking, it is not realistic, to detect all of these, big number of the species of bacteria, pathogens, which contaminated the food. Okay, I hope that you understand this difficulty. Okay, then we usually apply another strategy, which is the indicator bacteria or fecal contamination. So, as I said, I can say that we can find a variety of the pathogens in our intestinal tract. Also, that we can find them in our feces, fecal material. Then the Escherichia coli. Okay, this is a species of the intestinal the bacteria, uh, a species of bacteria is widely used as a fecal indicator because this bacterium normally inhabit the human and animal intestinal tract at a relatively high density. So all of you have this bacterium in your intestinal tract, and when you excrete the feces, I can say that discharge this bacterium to the I can say outside your body. Then its presence in water or food strongly suggests contact with the fecal matters, which may contain the human pathogens. Do you understand this explanation. If we detect the Escherichia coli in food and water, this is the evidence that food and water may be, I can say, contaminated with fecal material. And fecal material may contain the human pathogens as shown in the list in the previous slides. Then the food and water had the risk of infection. Okay, so you can see that I can say this. So I'd like to give you that explanation about this using this schematic. Okay, so Escherichia coli is the typical bacterium, typical species of the bacteria living in our intestinal tract, and it is I can say, always detected in the fecal material. Okay, and the of course how can I say some you may have heard the pathogenic strain of Escherichia coli, like Escherichia coli 0157, but it's very special. Other strain of the E. coli are not pathogenic to human. Okay, a limited number of the strains, very limited strain of the E. coli show the pathogenicity to human. Okay, but the you may sometimes find the E. coli as the I can say the standard or regulation of the food safety for the food safety. So that is sorry. This is not because the E. coli itself are pathogens. Okay, that is because E. coli is presence of E. coli indicate the contamination of the food and water with fecal material and human pathogens. For example, in the regulation of drinking water in Japan, E. coli must not be detected in 100 milliliter. No exemption. Okay, we never, I can say, detect any cell of the E. coli in 100 milliliter of drinking water. So you may, agree with me, the drinking water, our drinking water should not be contaminated by the fecal material. Do you agree? So like this, there are, similar regulation for food. Actually, it's depending on the, I can say, food type. But normally E. coli or total coliform sometimes are employed as the indicator. Total coliform is actually not the same as the E. coli. Total coliforms are used to be employed as the fecal contamination indicator because that we did not have a good method to detect the only E. coli from food at that time. Recently, that we can detect the E. coli only, with the development of the technology. That's why that we, I can say, normally use the E. coli as the indicator bacteria for fecal contamination of food and water. But in the past, or old regulations still, use the total coliform as the indicator bacteria. The total coliform include the E. coli, but total coliform also include the other bacteria, other species of bacteria, which are not related to the fecal contamination, fecal material. That is why the E. coli is more suitable indicator bacteria than total coliform. Okay, we'd like to move to the part two, food safety challenges, norovirus contamination in oyster. So norovirus is the leading cause of the food poisoning in Japan. So you can see, okay, please look at this figure showing that the annual cases of the food poisoning caused by the different type of the bacteria, pathogens like Salmonella, Vibrio, Clostridium, Staphylococcus, E. coli, Campylobacter, and Anisakis. Okay. So among them, the norovirus are the number one, norovirus caused largest number of the cases, throughout the recent 20 years, every year, and much higher number of the cases, okay, than the other, type of pathogens. And the norovirus food poisoning in Japan, uh, among the food, among the norovirus food poisoning in Japan, the a variety of the food have been implicated. Okay, for example, the seafood confectionery, composite prepared food, and others. So we cannot draw that all of the causative food, but a variety of the, I can say, food are implicated in the norovirus food poisoning. But when the only single unprocessed ingredient are considered, seafood account for the majority of the cases. In 2019, the 176 cases among the nearly 7,000 are called, how can I say, implicated, how can I say, how can I say, that caused, happened with eating the seafood. Okay? And of the 176 patients whose causative food was seafood, 127 cases were attributed to the bivalves, mainly oyster. So you may know that I can say that when we eat the raw oyster, I can say we caused the food poisoning. We had the food poisoning. In such instant, the most of the causal pathogens are norovirus. The norovirus in Japan, so I guess there are some you never eat the raw oyster. It's a kind of a custom or culture. Okay, but in Japan, we like eating the raw oyster, and some of us, even some of us, had the food poisoning. Okay. This is a very interesting story about the norovirus and oyster. The when we get the food poisoning, we how can I say um, have to use the toilet many times due to the severe diarrhea. And this when we I can say that discharge the diarrhea, I can say that we also discharge the viruses. So this is the our protect system, okay, of our body. So norovirus, grows and okay, multiple only in our body, and the uh, our body, force us to, I guess, excrete or discharge the such grown or multiplied, viruses, immediately by, causing the diarrhea. And that's why the diarrhea include or contain a huge number of the viruses. And the diarrhea, I can say the viruses, excreted with the diarrhea leads to the sewage treatment plant. And sewage treatment plant has the a high performance to remove the viruses. It, you know, some researches, tell us that 99% of the viruses can be removed there. This means that only one particle among 100, viruses uh, pass can pass this treatment processes. But only and such a small number of the viruses are, uh, getting into the water environment, such as river, and flowing down to the coastal area, and the sometimes that coastal area are used for the oyster farming. And oyster, I can say that always filtrate 5 to 34 liter per hour of seawater to collect microalgae as their feed. Okay, that they always filtrate the amount of the seawater for their surviving. Okay, but unfortunately the viruses is flowing near the area near the oyster farming. The oyster, how can I say, um, take the viruses with the sea water and accumulate it into their body. Okay, the viruses cannot cannot multiply in the oyster body, not only in our body. They can do only in your body, and that's why the oyster just accumulates the viruses, flowing down from our human society, and the consumer of that raw oyster enjoy the taste, but some unfortunate consumer I can say selected the contaminated oyster with viruses and get the infection and become the new producer or distributor of the viruses. So this is the circulation of the viruses between the oyster farming area, water environment, including the oyster farming area and human society, including oyster consumer. So this, circulation of the noroviruses were again, scientifically proved by our group in almost 20 years ago. Okay, we obtained that noroviruses in the hospital, I can say the infected people, the case of the the person infected with the noroviruses. In other words, we collected the norovirus from their feces. Okay, and we also get the oysters, how can I say, the viruses in the river and oyster farmed at the river mouth. And we check the genetical, similarity of the noroviruses collected in river, collected in the oyster, collected in the human feces, and finally found that the identical, viruses collected from the river, oyster, and humans. So this is the example, proof of the circulation of the viruses among people, river, and oyster. After that, we started the monitoring of oyster contamination of the noroviruses at the same farming area in 2040 to 2050 throughout 1 year. We collected the oyster weekly at the, I can say, oyster farming area, 3.2 kilometer far from the river mouth. And they have the one wastewater treatment plant at the 1.8 kilometer upstream of the river mouth. So we suppose that the virus is flowing down from this way, okay, around the 5 kilometer distance. And this is the procedure for the norovirus detection from oyster samples. First, we isolate the digestive tissues which accumulate the viruses, and we disrupt the cell of the digestive tissues and centrifugate the centrifugation, and after the centrifugation, we collect the supernatant, including the viruses, noroviruses. And we extract the RNA from the supernatant, RNA of the viruses, and we performed the reverse transcription of the RNA, viral RNA, and finally, quantitative detection of the target viral genes. Okay, this is the results containing the norovirus concentration in oyster indicated by red rectangle, and also that we show that norovirus concentration in wastewater indicated by the green diamond, and the number of reported cases in that area in each week indicated by the blue bar. So please, then we found that number of reported cases and the norovirus concentration in the wastewater and that in oysters were well correlated to each other. Increased, increased, and increased. Decreased, decreased, and decreased. And the number of reported cases of norovirus infection increased before norovirus started to be detected in oysters. Okay, this is the first positive result in oyster. Okay, but the number of cases already started to increase around here. So these results support the main contamination route, which is human to wastewater to oyster. Okay, human first. The viruses, excreted human contaminated oyster through wastewater. Okay, rather than the known one, the oyster, you know, um, is the main causative food of human food poisoning. Okay, so this is very, very important, I can say, message. Then, how can oyster contamination be prevented? Okay, so norovirus replicated only the human body and does not multiply inside the oyster. And not only there is a variety of the causal foods. I can say that the norovirus food poisoning. Okay, we have a lot of chance, of the norovirus infection, and infect people, excrete, discharge the viruses into the wastewater treatment plant. That wastewater treatment plant and similar treatment system can remove the most noroviruses, but eliminating it completely is difficult, as I already told. Then the norovirus originated from human feces and its discharge into the water environment is small in small amount together with treated wastewater. So this is the, I can say, general phenomena uh, uh, found in the non-epidemic period. So therefore, the E. coli contained in treated wastewater could be used as an indicator of oyster contamination. So as I said, norovirus, it's discharged to the, wastewater treatment plant, and some of them, pass through the treatment plant, and finally reach to the, oyster farming area. This is the common way or the common route of the E. coli, you know, uh, I can say that from the human feces to the oyster farming area. That's why I believe the E. coli can be still used as an indicator of oyster contamination with bacteria noroviruses. On the other hand, in the epidemic period, mainly in winter season, the secondary transmission or human-to-human transmission is enhanced. Then the norovirus cases are increased rapidly, regardless of the oyster contamination. The rise in norovirus cases due to the secondary transmission lead to more serious viral contamination in oysters because the larger number of the viruses are excreted from the increased, cases, and the larger number of the viruses can pass through the wastewater treatment processes and arrive at the oyster farming area. So it is difficult to prevent the oyster contamination due to a huge amount of the noroviruses arriving at the farming area. At this moment, the E. coli is no longer an effective indicator. because the E. coli discharge from the cases are same as in the non-epidemic period. The reducing the secondary transmission among humans is the only way to prevent the oyster contamination. Okay, by cutting off the number of the E. coli arriving, flowing down to the oyster harming area. So, okay, look, I'd like to show you that this result again. And we detect the noroviruses in wastewater in a green triangle at the higher contamination, higher concentration than normal level at a few weeks before the number of reported cases increased. So look at these 3 points. Okay. So this gap probably indicates the existence of the infected person outside the healthcare system. So please note that now, even if we get infection with the noroviruses, or not all of us, go to the hospital, see, see a doctor, because the, I can say, symptom, mainly the vomiting and the diarrhea, are not the, I can say, it's the symptom is severe, normally severe, but it continue only the 1 or 2 days. So some of us, decide, to take a rest rather than seeing a doctor. Then they recover, completely. Such case, they are not counted in this, blue line, but they also excrete the, viruses to the, wastewater treatment system. That's why the norovirus concentration in wastewater reflect that existence of the infected person outside the healthcare system. So this observation led to an idea for monitoring norovirus in wastewater to capture the early signals of epidemic of norovirus infection. So new system to detect the epidemic signals by monitoring norovirus in wastewater. So by monitoring norovirus in the wastewater, we can detect the early sign or signal of the norovirus epidemic and disseminate the information to society, enhancing preventive measures against transmission. So, so we cannot, I can say, stop the occurrence of the first case or second case of norovirus infection, but we can detect the occurrence, the number of the increase in the number of the cases at early stage by monitoring of the norovirus in wastewater, routinely. And if we can detect the early sign, early signal of the norovirus epidemic, so we I can say give the information the community to the community and recommend the preventive measures against transmission, expecting the reduction of secondary transmission, human to human transmission. So if it is, it works well, the significant, we also, get the merit, such as a significant reduction of the norovirus discharge to the water environment and production of safe oysters. This is our strategy. And this system has already implemented in the Sendai city, unfortunately not in Tsuruoka or Yamagata city. So they, how can I say, had this website, and once you registered in this system, you can receive the information or alert of increase in norovirus concentration in the wastewater. Also, although it is meaningful for Sendai citizens only. Okay, you are living in Tsuruoka, so the information is not specific to the the information is specific to the Sendai city. The it is just a reference. You cannot get the merit, from that information in Sendai city, unfortunately. And this system was also applied to the COVID-19 in 2020 and 2021 until now. Okay, so because the SARS coronavirus 2 as the causative pathogen of COVID-19 is detected in wastewater, just like noroviruses. We try to detect these viruses to catch to trace the number of how can I say patient of the COVID-19. And I can say that this application was tried in the other cities throughout this country, and some cities are still, how can I say, continue to use this system. And also how can I say that this system is applicable to other emerging pathogens such as influenza viruses, monkeypox viruses, which can be detected in human feces. So this system has the advantage of detecting pathogens shed by individuals who do not seek medical care. So as I told you that about norovirus infection, the not of not all of us, I know, I can say, visit the hospital when we get I can say, sick, especially that mild or I can say the mild symptom, and also that we are very strong adult, so we can tolerate, we have a tolerance to the symptom. So among them, our team, try to apply this system to antivirus resistant bacteria, ARB. The ARB is normally of the interest in the medical, setting like a hospital, because nosocomial infection caused by ARB are extremely serious for inpatient with other how can I say severe diseases. Sometimes such patient died due to the ARB infection, because that we don't have any good treatment, for ARB in some cases. But we believe that the normal or healthy individuals outside the hospital had the ARB without any symptoms, because the ARB normally that are not pathogens, or that's why it can infect with the inpatient in hospital with other severe diseases. Normal individuals are not infected by them. Okay, but the hospital in hospital setting, the doctors may try to detect the ARV from the patient samples, but we don't have any good we don't have any, I can say, chance to you know get the sample from the normal or healthy individuals. Then our strategy, to collect, to monitor the wastewater for detecting the ARV, because the people outside the hospital, excrete the ARV in their intestinal tract, every day to the wastewater treatment system. Okay. If we detect that some ARV in the wastewater, so we cannot identify the who have the detected ARV, but some of them, how can I say, must have the ARV even outside the hospital, and we can give that information about the ARV probably circulating in the outside hospital to the doctor in the hospitals. Okay, then the hospital can, I can say, select the, I can say, the antibiotics for treatment of the patient, with the reference of the that how can I say, the considering about the ARV circulating now in that area. So this is the one result, using our system to detect the ARV. So in this, study, we try to detect the clinically important ARV such as CALBA, ESBR, MDRA, MDRP, MRSA, and RVRE in municipal wastewater and hospital wastewater. So you can see that the number 24 by 24. So this means that every time CALBA were detected in the municipal wastewater number 1, but that ARV were not detected every time in hospital wastewater. Also, VRE were detected in the municipal wastewater, but did not detected in the hospital wastewater. So this means that the higher detection rate in municipal wastewater than hospital wastewater. This is just the, I can say, support our expectation that normal or healthy individual carry the ARV without any symptoms. In other words, these ARV were prevalent in the living environment. And the other another study shows that ARV detection in wastewater of Southeast Asian countries such as Thailand, Vietnam, and Cambodia. So you can see the detection rate of the VRE and SESVR Escherichia coli in this figure comparing to these 4 countries. So commonly to these 2 ARV, so Japan municipal wastewater shows that much lower detection rates than the other, Southeast Asian countries. So, generally speaking, that developing country had the higher prevalence of the uh, antibiotic-resistant bacteria in hospital setting. But there are no, I can say, reports on the prevalence of the ARV in normal and healthy individual in these countries. This study shows that clear difference or higher prevalence of ARV among them in Thailand, Vietnam, and Cambodia. So this is probably due to the improper use of the ARV for treatment of infectious diseases in these countries. This is common to the other developing countries all over the world. This is just I guess one example, but we would like to I can say continue this kind of their work in other developing countries. Okay, so I'd like to summarize this lecture. In the first part, I introduced that the risk analysis for ensuring safety. The zero risk is impossible, and trying to achieve it is not reasonable from a socio-economic point of view. Food safety should be managed on the basis of the acceptable risk determined through evaluation from various perspectives. In part 2, we discussed about the food safety challenges, norovirus contamination in oysters. With current technology, it is difficult to prevent norovirus contamination in farmed oysters. Reducing the number of the infected people, the source of the viruses, is the most effective way to improve the oyster safety. A wastewater-based monitoring system is already in operation as an early warning tool, and this idea has also been applied up to detecting outbreak of COVID-19 and emerging pathogens. Okay, that's all. Thank you for your kind attention.